All right, so like I said, we're picking right up where we left off before with our 2A goes to B plus C with our same H, S, and G calculations at standard conditions. I got three more things we're going to do. Okay, in this particular example, H and S were both negative. And when that happens, there's a temperature at which it'll flip spontaneity. So this is actually part 5. If we continue on with our other parts, part 5. We're going to calculate the temperature at which delta G flips signs. This will be worded like that, or at what temperature does it flip spontaneity, or what sign, or what temperature does delta G become positive or negative, depending on how it started initially. So we're going to calculate the temperature at which it flips signs. And that temperature was equal to delta H over delta S from our previous examples. So we plug in delta H. Delta H was minus 10.2 kilojoules per mole divided by delta S in kilojoule units. So we need the minus 0.1299 kilojoules per mole Kelvin. So the temperature at which this flips spontaneity, we can calculate from that. 10.2 flip the sign divided by 0.1299 flip the sign. So it flips spontaneity at 78.5 Kelvin. That's about dry ice temperature. Actually, it's colder than dry ice. Quite a bit colder, actually. But if this reaction mixture cools down to 78.5 Kelvin, the spontaneity will flip. So next up, this will be part 6. Calculate delta G at 250 Kelvin. So now we're getting away from a temperature that's standard conditions, right? So we're just calculating delta G. So delta G is delta H minus T delta S. Sometimes you'll see this written as delta G 0 sub 250K to designate that it's a standard, it's otherwise a standard calculation, but it's at 250 Kelvin. So at 250 Kelvin, we pull back our delta H, and our delta H was, let's see, pull up the board here. No, pull down the board there. Minus 10.2 and minus 0.1299. So minus 10.2 kilojoules per mole minus, in this case, 250 times minus 0.1299 kilojoules per mole Kelvin. So at this temperature, we can calculate delta G. So 10.2, flip the sign to negative. This means plus, because these are going to cancel each other out. So plus 250 times 0.1299. So I get a value of 22.28. Still not spontaneous, since delta G is positive. One more thing I want us to work here. So this would be part 7 in our numbering system. If the concentration of A is 0.125 molar and the concentration of B is 1.65 molar and the concentration of C is 0.510 molar, calculate the free energy at 298 K. So we're at non-standard conditions here. We are at standard temperature, so we have to calculate G at these non-standard sets of conditions. This is the G equation with Q in it, because these are the possibly non-equilibrium concentrations. So delta G equals delta G0 plus RT times the natural log of Q. So delta G0, that was 28.51. Plus R, which was 0.008314 kilojoules per mole Kelvin, times our temperature. In this case, it was 298, times the natural log of Q. Q is products over reactants, BC over A squared. So inside the set of parentheses, we have B, which is 1.65, times C, which was 0.510, all over A, which was 0.125, and that one gets squared because it's got a 2 coefficient over there. So we're ready to calculate this bad boy. Like I did before, I'm going to work right to left on this calculator. So 1.65 times 0.51 divided by 0.125 squared equals 53.86. Natural log of that, 3.99 times 298 times 0.008314 equals 9.88 plus 28.51. So I get a value of 38.39. Kilojoules per mole. So if you were asked about it, you would say non-spontaneous because delta G is positive. But how about this? At these conditions, is it more spontaneous than at standard conditions or less spontaneous at standard conditions? What do you think? So now we compare plus 38.39 to plus 28.51. So is this less spontaneous than 28.51? And the answer is yes. This is less spontaneous than at standard conditions. And that's because delta G here is greater than delta G0. All right, so we went through one big whole problem that encompasses our whole chapter. So out of this chapter, we need to be able to calculate H, S, and G from individual values in the table. We need to be able to calculate G from reaction enthalpies and reaction entropies. And we need to be able to calculate G based on delta G of formation table values. 3 different ways, again, to calculate G. We need to be able to relate delta G to K. So calculate K. We need to be able to calculate temperatures where spontaneity flips if H and S are both positive or both negative. And we also need to be able to calculate G at non-standard conditions. So these non-standard conditions might include changes in concentration and or changes in temperature. All of those are in play. You can change all of them simultaneously. R is always a constant. Delta G0 is a constant for the equation, but all the other stuff can be changed. Okay? Thank you for sticking with me on this, folks, and good luck.